number of protons and neutrons present in nucleus. Z means it is just a number of protons, and Mp is the mass of each proton and Mn is the mass of neutron. What is a binding energy curve? It is a graph that shows a variation between mass number and specific binding energy. Attractive forces that binds the neutrons and protons, which means the nucleons present in the nucleus together, is called as the nuclear force. Hello everyone, welcome to session 2 of chapter 13, Nuclei. This is Swati from Department of Physics, Vidyashram Tree University College, the Temple of Excellence, Mysuru. Dear children, in the last session we have studied about the constituents and properties of a nucleus. What is the basic terms that involve with the study of nucleus, that is a mass number as well as an atomic number, what it is represented as, and many more concepts. So in today's session, let us study more about nuclei. We shall start from mass defect. What is the meaning of mass defect? The name itself suggests there is a defect in a mass. But how to find the defect of mass of a nucleus? So that is what the mass defect concept is. So it is basically the difference between the sum of the masses of constituent nucleons. I told you in the last session what are nucleons. Nucleons means protons and neutrons are together called as nucleons. So it's the basic difference between the sum of masses of constituent nucleons and the actual mass of the whole nucleus is called as mass defect. If you measure the whole nucleus mass, you will get one value. Suppose if you find number of protons and number of neutrons separately, and if you find the mass of number of protons and number of neutrons and take the sum, you will get another value, but that value will not match with the exact value of the whole mass of the nucleus, and we will get some difference in the mass and we will call it as mass defect. How to find this mass defect? So let M be the mass of a nucleus, which means the entire mass of a nucleus, and it has a mass number A and the atomic number Z, which means A means number of protons and neutrons present in a nucleus, Z means it is just a number of protons, and Mp is the mass of each proton and Mn is the mass of neutron. So then the mass defect of the nucleus can be calculated as delta M. Delta stands for change or change in mass, which means the difference in their masses. So mass defect is denoted as delta M, which is equal to ZMP. What does it mean? Number of protons present in a nucleus into mass of each proton plus A minus Z signifies number of neutrons present in a nucleus into its mass, the sum of masses of nucleons. So this signifies nucleons mass minus the mass of the whole nucleus. So if we find this value or the difference we will get, we will call it as mass defect. Say for example, for carbon 12 atom, we have mass of the whole carbon atom is 12 atomic mass unit, mass of proton is 1.00728 atomic mass unit, and mass of neutron is 1.00867 atomic mass unit. So now, number of protons present in carbon 6, number of neutrons 6. So you can multiply that proton value with Mp and neutron value with Mn, then add those two values, take the difference between 12 and the value with what you get here, you will get to know what is the mass defect of carbon. So now compared to total mass of 6 protons and 6 neutrons, the mass of carbon 12 nucleus is smaller by 0.0957 atomic mass unit. So that is the difference value we are getting after finding its mass. This difference we will call it as mass defect. So next important topic is binding energy, which is denoted by EB. What is binding energy? It is the minimum energy required to split the nucleus into its constituent nucleons. To split the whole heavy nucleus into its constituent nucleons, that is into protons and neutrons, what is the minimum energy that is required? We will call it as binding energy. So this binding energy of nucleus we can define it in another way. The binding energy of nucleus is the energy that is released during the formation of a nucleus. So, which is denoted as delta EB is equal to delta m into c square, where delta m is the mass defect and c is the velocity of light in free space. So, next, we have specific binding energy or binding energy per nucleon. Specific binding energy is also denoted as binding energy per nucleon. How to define it? Specific binding energy is binding energy divided by its mass number. It is the ratio of binding energy of a nucleus to its mass number. We'll call it as specific binding energy. It is denoted as binding energy divided by A, where A is the mass number. So now, binding energy per nucleon. How to understand what is a binding energy per nucleon? It is the measure of stability of nucleus. The significance of specific binding energy is to say about how stable the nucleus is. So it's a measure of the stability of nucleus. If the specific binding energy is more, we can say that the nucleus is having a larger stability. So greater the binding energy per nucleon, that is specific binding energy of a nucleus, greater is its stability. So the basic understanding here is the significance of specific binding energy is to tell us how stable the nucleus is. Now we came to know what is binding energy, what is specific binding energy. So we are moving on to a next important concept, that is binding energy curve. What is a binding energy curve? It is a graph that shows a variation between mass number and specific binding energy. EB divided by A is nothing but specific binding energy. So it's a variation or a graph that is showing a difference between the specific binding energy of a nucleus with its mass number. So here you can observe we have helium, beryllium, carbon and oxygen, lithium, boron, nitrogen, and here we have iron. So we have mass number 30, 170, 240 here in the x-axis it is mentioned, which means that here iron 56 is having larger specific binding energy of about 8.75 mega electron volt. I told you about the significance of specific binding energy. Larger the specific binding energy, larger is the stability of a nucleus. So iron is the most stable nucleus, is what the conclusion or the first conclusion we can write from this curve. So the maximum specific binding energy is equal to 8.75 or 8.8 mega electron volt, which occurs for iron 56, and thus iron 56 is the most stable element, because with the help of specific binding energy we can conclude which is more stable. Larger the binding energy per nucleon, larger is the stability. So maximum specific binding energy is for iron 56, and hence we can say that it is the most stable element. Next, binding energy per nucleon of both light and heavy nuclei is very low. You can see here, these are the lighter nuclei and these are the heavier nuclei, and specific binding energy for lighter nuclei is low, and going forward we will get a curve which is gradually decreasing. So for heavy nucleus also the specific binding energy is low. The binding energy per nucleon increases rapidly up to mass number 20, and the curve contains peaks corresponding to helium, beryllium, carbon and oxygen. The peak indicates that these elements are more stable to their neighboring atoms like lithium, boron and nitrogen. You can see here the curve contains, see it increases rapidly up to mass number 20, and the helium nucleus, beryllium, carbon and oxygen are comparatively having high peaks to their neighboring atoms like lithium, boron and nitrogen, which means that helium, beryllium, carbon and oxygen are more stable when compared to their neighbors like lithium, boron and nitrogen. This is the region where we can observe the higher stability atoms or the nucleus of greater stability. From atomic mass number 30 to 170, the curve is almost flat, which says that the nucleus of the elements present here in this region have more stability. So that is point number 4. For the nuclei greater than 170 mass number, the specific binding energy gradually decreases. So what are those elements which are having a less stability or lesser specific binding energy? So heavy elements such as uranium-235 have still lower specific binding energy, hence they are highly unstable. They continuously emit their radiations, they undergo disintegration because they are having less stability. You can observe here in the curve, after 170 again the curve decreases, which means a heavy nuclei such as uranium-235, they are very less stable. Since they are less stable, they undergo continuous or the spontaneous disintegration and they are called as radioactive elements. So next we have the curve shows that the lighter nuclei and the heavier nuclei having smaller specific binding energy compared to a medium mass nuclei. Thus and hence, when a heavy nucleus break into two lighter nuclei, it undergo fission reaction, or when lighter nuclei they combine together to form a heavy nucleus that undergoes fusion reaction, the end products have higher binding energy and large amount of energy is released. You can observe in this curve, here we have lighter nuclei, here in this region we have heavier nuclei. So these heavier nuclei undergo fission reaction, they split into its constituent nucleons, and here the lighter nuclei combine together to form a greater or heavier nucleus, that is fusion reaction. So in both these reactions, the energy released will be enormous. So the next important concept is nuclear forces. So we have studied in our first PUC about the fundamental forces in nature, where we had gravitational force, strong nuclear force, weak nuclear force and electrostatic force. So among these four forces, we know that the strong nuclear force is strongest among all. So what is this nuclear force then? So the attractive forces that binds the neutrons and protons, which means the nucleons present in the nucleus together, is called as a nuclear force. So strong nuclear force is basically helpful in holding or in binding these nucleons together. So it is actually greater than, many times greater than electrostatic force as well as the gravitational force, and hence it is concluded as the strongest among all fundamental forces. Let us now list out the characteristics of nuclear forces, which are very important, and this question is also very important examination point of view. The first characteristics is they are strongest force in nature. As just now I said, it is strongest among all fundamental forces in nature, and these forces are charge independent, irrespective of the charge, that is protons having positive charge and the neutrons having electrically neutral, and irrespective of these charges, the forces helps those protons and neutrons to bind together, and hence they are charge independent. They are very short range forces. Why they are short range forces? Because we know atom is a fundamental particle, nucleus is inside it, and it consists of protons and neutrons, which means it is happening the force that is existing between two fundamental and the finest particles, that is protons and neutrons, which are having a less distance of separation. So they are actually a short range forces. So nuclear forces are attractive in nature. Since they are attractive in nature, they can hold these nucleons together. They are saturated forces. So what does it mean, saturated forces? It acts only within certain boundaries. It acts among its neighboring atoms, so it is saturated. They are non-central forces. It is not restricted that they are acting between the centers of each particle, or protons and neutrons, or neutrons and protons. So they are non-central forces. They can act among the neighbors in all the directions. They are not central, and they are exchange forces. Why they are called as exchange forces? Protons can be converted into neutrons, neutrons can be converted into protons under certain conditions, that is by exchanging particles called as pi mesons. So since they can exchange their characteristics, they can called as exchange forces. They are dependent on the spin and the orientations of protons and neutrons, and these are the characteristics of nuclear forces, a very important question. So dear children, in today's session we have discussed about the mass defect, binding energy, specific binding energy, as well as the binding energy curve, which is very important, nuclear forces and its characteristics. In the upcoming sessions we shall study more about nuclei. See you all in the next session. Thank you.